So the last talk of this morning is by Leon Balents from here, and he'll talk about kinetic equation for Phonon Hall effect.
Okay, thank you. This will be a little bit of a change, not just from the last talk, probably from all the talks. I'll tell you about some ongoing work that's being done with our chairman and Leo Mangiol, who's probably also here somewhere. Those of you who know me are used to me giving probably rather experimentally connected talks. This is not going to be one of them, okay? I had perhaps overly optimistic views about what would get completed by the time this talk came up. So what you're going to get is a story that is incomplete, but I find it interesting. Maybe some of you will. But the pessimistic view, I'm just going to cut it off so you don't criticize me about this, is that we're just trying to solve an already solved problem using it, which is just a free field theory, so it couldn't be more trivial than that. Doing it in a different way just because we're stubborn and not even fully succeeding. Okay, but the optimistic view, I've learned we should try to be optimistic, is that we're going to formulate an exact semi-classical kinetics for time reversal broken bosons, and hopefully which will be a useful framework for more complex things. And from my personal point of view, I'm looking for some intuition for some results that are not at all intuitive to me. So just to set the stage, tell you about something that I guess everybody should know. I teach it in my condensed matter class, the anomalous Hall effect. Intrinsic anomalous Hall effect we know arises due to Berry curvature of bands. And whenever we talk about something like Berry phase, Berry curvature, we're always talking about kind of quasi-adiabatic motion under the influence of weak or slowly varying forces, so that a particle that we're studying kind of stays almost in an eigenstate. And when that happens, we can, I don't know what this thing does, nice, okay. When that happens, we can kind of sort of project out all the inner band effects to obtain an effective description of a particle moving within a band. And these are the famous semi-classical equations that, bits and pieces have been around for, a good more than a half century, but in the last couple of decades, Chan Yu and others kind of put them all together. And in particular, for the anomalous Hall effect, what's important is this anomalous velocity that gives a contribution to the electron velocity proportional to the force, because it's the rate of change of momentum. And you'll notice that the anomalous Hall conductivity here involves the bare electron distribution. So this effect, the current in the anomalous Hall effect, doesn't come from change of the electron distribution. It comes from the change of the velocity. So we've seen already a number of talks about thermal Hall effect. As theorists, motivation to study thermal Hall effect is it gives a unique window on topological effects in solids in particular, and ideal fully gapped topological phases. Kitaev taught us that it actually gives a way to measure the chiral central charge. When we're studying insulators, if we see something chiral, we see something which is sensitive to magnetic field, it's natural to assume that this must come from spins or in some way from electrons that are the things that are sensitive to magnetic fields. But as Takagi-san told us this morning, there are many experimental evidences in a variety of different physical systems that actually most of the time the thermal Hall effect seems to come from phonons, as normally does the longitudinal thermal conductivity, even a lot of the time in electronic materials. With that motivation, one would like to ask about how does a lattice carry heat conductivity? Just conceptually thinking about it, you can think of two ways that can happen. there could be, it's very similar to the discussion of Hall effect in metals. For for decades there was a confusion about whether anomalous Hall effect arose from kind of a scattering mechanism where electrons will scatter preferentially, let's say to the left or to the right, skew scattering or side jump, various mechanisms like this, or it arose from these intrinsic effects like the Berry curvature. Heat transport is, if anything, more complicated than charge transport, but we can certainly imagine both types of mechanisms going on. And I like to think about it in terms of kinetic equations. Anything involving Berry phase has to do with the terms on the left-hand side of the kinetic equation. These describe how the particles kind of flow in free space without scattering events, and anything to do with scattering will sit on the right-hand side. And both of these are viable. I don't want to really talk about in this talk what's more important in different experiments. Just to say we have probably collisions are pretty important in a lot of these experiments, and we have some prior work on that. Others in the audience doubtless do. In this talk, I'm going to be a kind of a purist. This is very much a purist theorist talk. I want to talk about the intrinsic effects. So I will talk about phonons, and we'll think about low temperature, so where only acoustic modes will be important. Acoustic phonon is really described by a massless free scalar field, or three of them in 3 dimensions, and they're in general can be coupled. So we have some kinetic energy, we have some potential energy described by some elastic constants. And that doesn't break time reversal symmetry. To get a Hall effect, we need to break time reversal symmetry. At the Lagrangian level, we need something with a time derivative. And taking into account the other symmetries of a crystal, the lowest order terms you can write involve 1 time derivative and 2 space derivatives. And in general, there's some structure here. Because you can integrate by parts on the time derivatives, this has to have some antisymmetric structure in the indices on the phonon fields U. Okay, and this in general, this is kind of in general what you would expect to be the lowest order term you could write for time reversal symmetry in many massless boson systems. So we could, I don't know if this is really important in very real experiments on phonons. One would like to think it could be achieved somehow, but regardless, maybe it could describe other bosonic modes. Maybe it's more. It's nicer to write this in the Hamiltonian form, so you can just, in the usual way, find the canonical momentum, pi here, and what you find is, it's kind of easy to think about this if you just were to Fourier transform in real space. All the space derivatives just turn into constants, and you can see this is very similar to how a vector potential would couple to a coordinate of a particle, and indeed you can think about this as sort of a k-dependent A is representing kind of a k-dependent magnetic field, which is related by this parameter, the Hall viscosity. It's kind of natural then that this will allow, if you were to try to find the eigenstates of this problem, they'll have some Berry curvature, and this will allow a thermal Hall effect. Okay. So this is a quadratic problem. I mean, it looks like a textbook problem you could give your undergraduate solid-state physics class. Maybe if you simplify some of the indices. I think it's a fair question to say, okay, just shut up and calculate, as Shankar likes to say. Somebody told him, but I can't remember who told him to shut up and calculate. Maybe somebody's heard this story in the audience. So, of course, somebody did that. There's a very nice paper by Chin et al. From more than a decade ago, where what they do is they employ the Kubo-Luttinger formulation of thermal transport, which introduces this kind of fictitious gravitational field, and then writes thermal transport quantities as a linear response to gradients of that field. And they indeed were able to derive a result for the thermal Hall conductivity. And it looks kind of like what you would want. It looks, it involves a Berry curvature of phonon states. and some energy integral with Bose functions in it. It looks very semi-classical. Now, the derivation is not at all semi-classical. It's just an exact solution of this model via a Kubo formula, more or less. And yet, the more you look at it, the more confused you get, at least me. First of all, you notice that it's an integral over energy of something which itself is an integral over energy. So it involves some double integral over energy, which is a little weird. It also involves this Berry curvature, and if that kind of is natural to think this is due to some anomalous velocity of the phonons, but there are no real forces on the phonons. They're just in the presence of a thermal gradient. So what's the force on the phonons? And finally, I would point out this very tiny superscript here, TR, which is transport. If you actually just use the Kubo-Luttinger formulation to calculate this thing, you get a very different answer, which is very badly behaved physically. It violates Onsager relations. It diverges at low temperature, does many, many bad things. So the trickiness arises from a subtlety, which is known as energy magnetization. So we're working in a model with this Hall viscosity that breaks time reversal symmetry. And so because we don't have time reversal symmetry, in principle, even in equilibrium, currents can be flowing, in particular currents of energy. Now, in equilibrium, in a static state, they need to be divergenceless. So in general, these equilibrium currents can be written as the curl of something. That something is time reversal odd, and we can call it an energy magnetization since it's an energy current. And this can be sort of thought of as an equilibrium quantity in equilibrium or quasi-equilibrium. We perturb it a little bit. Obviously this thing should be zero outside the sample. As a consequence of this, if you consider take a surface that cuts entirely through your sample. So experimentalists will always kind of measure the total current passing through a sample. We just count the total current through here, and the total flux of the current through the surface is equal to the line integral of the energy magnetization around the loop, which is obviously zero. Okay, so these kind of magnetization currents can never give a contribution to the total current. In that sense, they're non-transport. It doesn't mean they're not real. They can be present. In a large sample, or really in the thermodynamic limit, these currents are, of course, going to be zero everywhere in the interior, because otherwise the magnetization would have to be not constant. But in general, they'll be in equilibrium, they'll be at the surface. Out of equilibrium, they're not necessarily at the surface anymore. So these things need to be subtracted from the transport current. So that's what this transport current is. I emphasize that it's not that the transport current is the actual current inside the sample. It really isn't. The thing you normally would calculate with a Kubo formula, what you would write down as the current operator, is the real current flowing, but sometimes in the situation of transport, that's compensated by something at the boundary of the sample. So it's kind of subtle. It means that to get the right transport thermal conductivity, you need to know the energy magnetization. It's a little tricky. In principle, it's an equilibrium quantity. But in equilibrium, in the thermodynamic limit, where as theorists we like to calculate some intrinsic quantity that's not dependent on the boundary, it has to be the magnetization has to be constant if it's an intrinsic quantity in a translational invariant system. If it's constant, then the resulting current is zero, and it's only the current that's physical. So it's quite tricky to calculate, and Chin et al. Came up with some scheme to calculate it, which is quite involved. Within the Luttinger formulation, you have to evaluate this, which is kind of a Kubo response function. This doesn't determine the actual magnetization. It determines this m tilde quantity, and the actual magnetization is given by solving this temperature-dependent differential equation, given that quantity m tilde. Then once you know it, you can relate the Kubo linear response quantity to the transport thermal conductivity. Okay, so that's why these formula are so weird looking. Okay, and what can I say? I don't like it. Okay, there are a lot of things you could wish for. These are kind of my wish list. All right, which is the motivation for dragging others into this project. First of all, I don't like the fictitious Luttinger gravitational field because it's not real, and we shouldn't really need it. You know, whenever we do electrical transport, we often get actually involved in the subtleties of the difference between the chemical potential and the electrochemical potential. But actually, the electrostatic potential is a real thing. Electrons feel electric fields. They feel forces. And you know, there's actually a separate equation to determine it, Poisson's equation or whatever. You know, that's determined by charge dynamics. So Luttinger's gravitational field is completely made up. It's just something that we put in by hand. So we would like a better description will simply involve the non-equilibrium distribution of electrons. This result has every appearance of being semi-classical, given that it involves this natural quantity, the Berry curvature. And, you know, if we go back to the electron case, we can derive the anomalous Hall effect using Kubo formula involving lots of fun manipulations of Green's functions, et cetera. But we can do it in, you know, in one line using the semi-classical dynamics. So it would be a lot more intuitive if we could understand that way. And finally, you know, if we could hope to actually know what these inhomogeneous energy currents look like. So that's the wish list. And there's kind of a clear path towards arriving at that, which is to really understand the kinetics of our bosons, of our phonons. So what kind of things we want? Well, we don't want to do worse than this previous work. They're just an exact solution. So our method should be exact at long wavelengths, which is what's assumed in linear response. We want it to be semi-classical. It should reduce to some dynamics within the bands where Berry curvatures are a natural quantity. And it needs to, since we want to be able to determine these currents, and in particular magnetization currents, it needs to allow for spatial gradients. So we'd like to accommodate all those ingredients. Okay. So there's a procedure that's sort of known for doing this. Some of you probably know how to do it for electronic systems. I don't think people are so familiar with how to do it for phonons, at least certainly with the Hall viscosity. We seem to need to invent a lot of things. So basically it happens in 3 steps. I'm going to sketch how this thing works, at least so far as we've made it work. So first we can derive an equation for the 2-point expectation values that it follows. Then we can employ what's called the Wigner transformation, which connects these 2-point expectation values to distribution functions, really quantum versions of distribution functions. It's something like a local density matrix. And then we can try to diagonalize this to make it semi-classical. Okay. So the first step, you know, is fully exact, so it's sort of straightforward. We want to take a Hamiltonian which allows for spatial dependence. So all these coefficients, the viscosity, the elasticity, the mass density could be varying in position. Okay. And then we define this kind of kinetic momentum. So our degrees of freedom are 3 coordinates and 3 momenta. So that forms in 3 dimensions, a 6-component Bose field, and we can consider its 2-point function. Okay. So lots of physical quantities are expressible in terms of the 2-point function, like the current, the kinetic energy, et cetera. So that's why it's a useful object. If we know how it evolves, we can calculate many things with it. Since it's a free field theory, we can take its time derivative, just using the operator equations of motion, and you'll find that it evolves via some operator acting on the first coordinate and some operator acting on the second coordinate. And this is sort of like a dynamical matrix. It's some set of differential operators, acting on these fields. Simple. So the second step is this Wigner transformation. So this is how correlation functions in quantum mechanics are related to distribution functions. So you go from these two coordinates, R1 and R2, to a center of mass x and a relative coordinate little x, and then Fourier transform with respect to little x, like this. So this, you can think kind of the center of mass describes slow variations, and the k would give like the momenta of quasi-particles, of phonons. So this you can do exactly, and then an approximation comes in, which is that we want to study slowly varying systems. So then we treat the derivatives with respect to big X as a small parameter. Okay. And so doing that, okay, all the intermediate steps are fairly complicated and nasty, but it turns out the thing can be rewritten like this in a way that's so simple it looks almost trivial. So the time evolution of this kind of quantum distribution function involves a commutator with this matrix K. K is kind of like a local Hamiltonian. It's the kind of dynamical matrix for the phonons. If I had a translational invariant system, K would only depend on momentum, and it would describe the matrix giving the time evolution of position and momentum coordinates of the phonons. So it's multiplied by a factor of I so that its eigenvalues will be the frequencies. So there's a term involving the commutator of this, which is basically describing the fact that since we have two fields here, each of them could be oscillating. If we take two fields that are at kind of representing different phonon bands, then they don't oscillate at the same frequency, and that combination oscillates, whereas if we take them at the same band, it doesn't oscillate, and it's a slowly varying degree of freedom. And then what's left is kind of neat looking. It kind of looks a lot like a Poisson bracket. Involves derivatives of this thing K acting like a Hamiltonian, and derivatives of the distribution function. Okay, and we kind of write it for compactness. We introduce some sort of epsilon symbol that puts these terms together. Okay. So that's the first step. Before we go further with it, we can just try to ask if we understand it. Does it make sense, this thing? So this is the quantum kinetic equation, and there's no real approximations apart from going to first order ingredients. You could go higher, would not be problematic. For the phonon system, it will stop at second order. That will be the full equation. So the first thing you can ask is what happens if we have no gradients? Then this term vanishes. One of these derivatives is always with respect to position, so this just drops out. And then the solutions are any matrix F for which this thing vanishes. I should say this isn't really the commutator. We're hiding something. This is kind of like a commutator, but with a transpose in it. Sorry. But anyway, it's almost like a commutator. Think about it like a commutator. The solution of this is basically F is an outer product of eigenstates of K. So you know things that our eigenstates will commute with the matrix. This is kind of natural. It means that F is sort of diagonal if we don't have any gradients or any forces. And indeed, you can check that these Fs obey certain physical constraints that are due to the reality of the phonon field and their commutation relations that relate it naturally to an occupation number. It actually has dimensions of energy times an occupation number. So if you know F, you know the distribution of the phonons. So another good thing to check is energy conservation. Can you understand that? This is kind of a neat feature of semi-classics. You can define an energy density in the full phase space as a function of K and X, and it's just simply related to some trace of this distribution function, and it's pretty straightforward to show that the time derivative of this is minus the divergence of some phase space current. So it satisfies a continuity equation, and you can define some current in phase space. Okay, step 1, 2 done. Step 3 is the bad one. Yep, 5 minutes left. So we got this equation what do we do with it? Well, you know, we could stop with the fancy manipulations here. It's an equation for a matrix. We could just solve it. Okay. But you know, that's not getting us too much physical insight, although it would be enough, you know, on a computer to solve, I think, for inhomogeneous systems and really see where these currents are, et cetera. Okay. But instead, we can use the fact that, you know, when the gradient term is 0, the solutions are just these diagonal ones. So they'll locally follow if the gradients in the Hamiltonian are weak, or we impose weak gradients externally, the solutions will locally follow this eigenform. And what we can hope to do is then perturbatively eliminate these off-diagonal parts of the distribution function. And indeed, you know, we can write a general distribution in terms of diagonal and off-diagonal parts, and we know that the off-diagonal part starts at first order in the gradients, while the diagonal part starts at 0th order. And so, for example, you can find an equation for F1 in terms of F0. Then you can plug that back in and get F1. Then you can find F2 in terms of F1, et cetera. And this process can be iterated to arrive at a closed equation for FA. Okay. So, as I said, this is somewhat of a different talk than I usually give, especially to this kind of audience. You used to hear me talking about frustration, which I did talk about at the teachers' conference. For this talk, I have a different sort of frustration. That everything I presented looks rather simple, but behind the scenes, it somehow blows up in some horrible way. And the culprit is that basically phonons are not intrinsically conserved. The only thing really conserved is energy in a phonon system. And so the kind of fundamental dynamics doesn't really have a conserved charge associated with it. The dynamics of this phonon system of position momentum is described by some non-Hermitian matrix K. And it's this thing that defines the eigenstates whose Berry phase, Berry curvature we want to follow. So in particular, K has different left eigenstates than right eigenstates, and they're related by some matrix, which itself depends on position and momentum. And so all the things you're kind of used to, you know, that you take phi star gradient of phi, that's pure imaginary. It's not true for non-Hermitian eigenstates. And so this derivative of this damn matrix C proliferates everywhere and interferes with simplifying things. I'm sure it must work eventually, but we struggle to find how to make things work nicely. I'll just tell you what works so far. So we can write the first order kinetic equation, which corresponds to sort of projecting the quantum kinetic equation onto bands and ignoring some higher order corrections and gradients, and it looks like you'd expect. We had a Poisson bracket of these matrices. They become Poisson bracket of the scalars. Okay, so this is nothing but collisionless Boltzmann equation. Okay, and you may wonder, you know, where's the Berry curvature in this? Well, it doesn't enter till higher order. If you think about in the kinetic equation, the Berry curvature should enter the velocity of the particle. It's proportional to some force, which is a spatial gradient of some potential, and it also multiplies the gradient of the distribution with respect to coordinates. So it's higher order in gradients. And in fact, it didn't enter the anomalous Hall effect for electrons. We don't really think that should be important. But there's terms that I would not consider presentable. Yeah, I'll finish, don't worry. The current is a little more interesting. So there's kind of the natural term in the current. This would be, if you look at the spatial component of this phase space current, it's just the usual group velocity, d omega dk times the distribution. But on top of it, there are higher order terms that look a lot like anomalous velocity. They involve a derivative of the distribution function and some object kind of like the Berry curvature. Just remember that F has the dimensions of energy, so this kind of involves some, it looks, it's actually more like orbital magnetization than Berry curvature, but still this is kind of promising. At this level, we could do the Kubo linear response function with this formalism, and it recovers exactly the Kubo linear response formalism that you'd get just by direct microscopic calculation. Okay. And the advantage here, we could do it without a gravitational field. We just directly calculate with a temperature gradient. Okay. But I remind you that that's not the transport thermal conductivity. So calculating this energy magnetization, unfortunately, is hard, and we haven't succeeded in doing it yet. Hopefully it will come. One thing I can say is that although I kind of want to avoid the gravitational field, you could incorporate it here. It incorporates in a very nice way. Just to remind you how that works, Luttinger multiplies the Hamiltonian by some scalar function such that its ratio with temperature is the same as a spatially varying temperature. And that's more or less the idea. If we do this form, so this is a less general form of a spatially dependent Hamiltonian than we have taken, but we can specialize to this, and this can actually be kind of gauged away into just gradient gauge fields in the kinetic equation. So basically, it has the feature that the structure of the eigenstates locally is related by a similarity transformation to those in the constant system. And with that, it's possible to represent the energy currents explicitly as some linear function of a gradient of the gravitational field. You know, in principle, from this, it's possible to extract the energy magnetization. In practice, at the moment, this is too complicated. Okay, so unfortunately, that's the end. It's a talk without at least super satisfying results, but I think the procedure is kind of fun and interesting. I hope maybe you found it mildly entertaining. I'll stop. Thanks.
Nice talk. Are there any questions?
Just a naive question about the energy magnetization. So if you have a system with a constant energy magnetization, then there's going to be a surface energy current.
Yes.
Which that presumably is a physical thing.
Yeah.
Right? So there's some non-zero, you know, like pointing vector for your phonons that's
absolutely.
So what does that? I mean, so does there have to be is there something interesting going on the surface? Or
yeah.
Is that something that has some physical?
I think it should be observable. Yeah. I mean, there have to be some. They're not bound modes because it's a gapless system, but there has to be some surface energy current, some chirality of the phonons at the edge, I guess. I mean, that's what we're hoping to be able to calculate out of this. I mean, in principle, we already have the technology if we wanted to do it numerically. But
so actually, yeah. So if you just have a, just masses and springs, numerically, you can calculate this thing. Is there a situation where you actually do have a big, sort of delta function of current flowing on the surface?
Well, I think there has to be. Once you have to break time reversal, you have to have this viscosity, but I think there has to be. But I haven't done the calculation.
Okay.
Yeah, we haven't, as far as I know. My collaborators are sneakily calculating behind my back.
All right, thank you.
Yeah. That's I kind of want to understand what this thing is. Yeah.
It's just a naive question. So, I don't know how to do this, but is there any reason why you specifically avoided Keldysh?
Avoided what, sir?
Keldysh.
We didn't need it. So maybe I don't need to show anything. Let me just say, so the observables we want, like the current and the energy density, they're all equal time observables. So it's sufficient to have an equation which governs the equal time 2-point function. And it turns out we can write a closed equation for that. And so it's more direct. If you were to use Keldysh, the standard procedure is to also do Wigner transformation in time, and
That's
there will be
correct,
some
yes.
integral required over the internal frequency to get equal time quantity. So this kind of circumvents that.
I was just wondering whether that may help you to get this energy magnetization contribution. I'm not sure.
I don't see any way in which it makes things easier. I think it makes things more complicated. Yeah.
All right.
That was the first thought, in fact. And then at some point we realized we could simplify by doing this. Keldysh is the standard route to kinetic equation, but there's more approximate steps that are made. Yeah.
Thanks for the nice talk. I'm trying to understand the talk in the context of the introduction, which was to understand the transport of chiral bosons.
Right.
Now, in this setting, it seems that you're talking about real bosons that are moving, and one wants to understand their Hall response. But would this change if we considered chiral phonons? Was that captured inside this in this formalism, or do
define what you mean by a chiral phonon? I mean, these are chiral, I guess. Usually when people talk about chiral phonons, they're talking about like optical modes or something, where you can, at the zone center, there's some kind of simple way to make a description. Those at, at low temperatures, those are not going to contribute to transport.
Okay.
So here we're focused on acoustic modes, and k = 0 is kind of not a very well-defined point there that corresponds to just uniform translations of the crystal. So we always have to stay away from k = 0 and study, the modes that are actually dispersing. They're chiral in the sense, with the Hall viscosity, there are different velocities for right and left circularly polarized phonon modes. If you didn't want to do transport, there's a simpler signature, which is acoustic Faraday rotation, which is related to the Hall viscosity. Maybe this addresses your question somewhat.
Okay, thanks.
Yeah.
Hi, Leon, I have a naive question. So you have this phase space current, also interpretation of the moment space components. What's the physical consequences? No.
Oh, well, under applied force, the particles change their momentum. So there's a flux in phase space. That's all.
Okay, yeah.
Yeah. For physical transport, we were going to want to integrate over K. The total thermal current is a K integral of this phase-space current. Although that phase-space current is kind of semi-classical, you can actually show that if you take the K integral of it, it gives the exact thermal current. That's like true beyond the gradient expansion, which is an accident, I think.
Right. So Chin's result it involves a Barry curvature of only the right eigenstates. Is that correct?
Yes.
So do you believe this result is correct or incorrect?
I think it's correct.
Then how do
The
you?
left eigenstates are very simply related to the right eigenstates. So there's you can check. I mean, you can go between the two. There's not really a. Yeah. I don't think there's another gauge invariant quantity which you can define. I mean, we've checked the calculations. At least they're correct. Okay. Yeah.
I wonder if you need to impose some local equilibrium conditions to obtain the Barry curvature contributions.
I think we need to impose some local equilibrium condition to get the energy magnetization. The Barry curvature is just a property of the dynamics. It should not really require any particular equilibrium assumption. So the approach we're taking is to try to really derive the kinetic equation, not assuming any equilibrium per se. You can see this equation doesn't require you to assume that. You can do sort of consistent expansions around any state which is stationary for the 0th order term here, and that's any distribution of the phonons. So I think any phonon distribution which is smooth in phase space could be expanded around. You know, with collision and things, some of them will be highly unstable, but
So that
here.
I see. So that justifies for the energy magnetization. You kind of introduce the gravitational field.
Yeah, at the moment that's a crutch. I mean, I think it's nice that'll allow us to connect more directly to Chin et al. But the hope is to eventually get it out without the gravitational field.
Thank you.
I have a rather silly technical question.
What question?
A rather silly technical question.
Silly technical question.
Okay. So when you go from the Lagrangian to the Hamiltonian, there's an I that is somehow missing. So I'm just curious whether you just hid it somewhere or.
Oh, well, I wrote the Euclidean Lagrangian.
Oh, I see. So
why.
it's just there somewhere.
That's
Okay.
my own perverse preference for showing Euclidean Lagrangians.
Okay.
Euclidean Lagrangian, you get this I. You know, the real Lagrangian would have some minus signs and no I.
Okay.
I like the I because it gives you a hint that this is something topological. It's related to phases.
Okay.
That term in the action, in the exponential, in the path integral is always imaginary.
All right.
Okay. That's
Thank you.
because in the real time path integral, it's e to the is. You know, so I want to see the I. So.
Hello. Very nice talk. So about your to-do list, you mentioned both energy magnetizing and also computing edge current. But I'm assuming like if you can already like compute edge current, I don't need eventually to do this magnetization, isn't it?
Right. That's true. There's more information in the edge current than in the inner. You have a distribution of that current.
Right.
You can
Right.
try to answer the question like Charlie asked, what are these phonons actually doing at the edge? Yeah. That's my preference would be to see that, get the actual current profile in a
Okay. But that do I still need to? So for this part, I can do it. Assuming eventually you are going to reach there by this kinematic equation, or do I still need a Luttinger trick or for this edge current thing?
Edge current, we don't want the Luttinger trick, actually. We need an edge. So the Luttinger trick just multiplies the Hamiltonian by a spatial constant. We can't remove the topological phase that way. So
Right.
So the natural thing will be to make the Hall viscosity space dependent. And we have outside the sample, the Hall viscosity is 0.
I see.
The time reverse is not broken out there.
I see. So eventually, if we have a fully semi-classical picture, we don't need this energy magnetizing anymore. Right?
Yeah, maybe we don't. Yeah.
Okay.
I don't want to be
okay.
judgmental. Maybe you like it. Yeah.
Okay. Good. Thank you.
Sure.
We're out of time, but if there is one urgent question, I can take it.
Doubtful.
Okay, thank you very much, and thank you all the speakers today.